All right. Hey. So my friend Brielle and I are here. We're going to go through some activities and have a little discussion about it. I thought it'd be a lot easier to do it this way than to be talking to myself. And Brielle may jump out in a couple minutes when she has to run. But Brielle, thanks for being here with me today.
Thanks for having me.
What we're going to do is we're going to bring up some different activities. And I'm going to show you some stuff that I've done in the past. And this could give some schools ideas for things they could maybe do. And it'll also give you and I a chance to talk shop, So thanks again for your time.
Awesome.
All right, so I'm recording. I'm going to turn my camera off. Get rid of the northern lights back here. And let's share my screen. Share. I think what I'll do is I'll share one of my desktops and then I'll drag pictures and stuff up into that spot. Pick desktop 2. And I'm going to share sound as well. I never hit optimize for video clip. I feel like whenever I do that, it doesn't always work out. It's only good for video clips when you share a full screen video clip. All right, so awesome. So I'm recording over this screen here. I had a kid in middle school that I taught in 7th grade. I thought for sure he was going to end up in jail. Great kid. And then years later, I bump into him on Facebook and he's building remarkable furniture.
Oh,
and
that's amazing.
We get back together and he helps me build this 12-foot long farmhouse table for my wife as a wedding gift. That's
incredible.
And these were pictures in the background on my screen here. Can you see that door?
Yeah, those are amazing. And that's a table?
These are initial drawings he sent me, some things that he does just to kind of show off to me that he didn't go to jail, that he ended up taking stuff we learned in school and doing something cool with it.
I love that. That's so incredible.
Yeah, I did hear something about you at a farmhouse, but we'll talk about that later.
Yes.
All right, so let's get my photos up here. And what am I going to bring up first? So I guess I'm going to start with some if I think of the human design world in 7 areas, as they do in those standard 8.2. There's communications activities, construction activities, manufacturing, transportation, biotechnology. Biotechnology could be things like agricultural or medical, and what are the other areas? Transportation, communication, power and energy. So for the 6 or 7 areas of the human design world, that's why I like to think of how activities can be categorized. Other people sometimes will categorize them by engineering fields they might be involved in. But let's see. I'm going to start with something from middle school here. You know what? Let's do this one. So here are there's an activity I would often use. You can see my photos here.
Yeah.
You see that cut on my hand?
Yes.
Yeah, gross, right? I just finished teaching a safety lesson to a bunch of Girl Scouts about razor blade safety. And as soon as I was done the lesson and they were getting ready to leave the room, I had a pack of drill bits I wanted to open up, and I did exactly what I said not to do in my lesson. And I tried to open up the little twist tile there, and then the razor blade went right in my side of my hand.
Jeez.
But if you see this pink styrofoam here, you ever seen this stuff before? The pink polystyrene foam.
Yeah.
Yeah, that pink or blue foam. We all work with it. It's cheap. It's soft. It's really safe. And so in that creative design course, I teach a lot of classes. Instead of we're learning to use tools and machines for the first time, we'll use something like foam like this, And
no, it makes sense.
Yeah, learn to sand with it, learn to paint it. You can use different tools on, but that's a hot wire styrofoam cutter. And that was a design challenge where everybody gets a block of foam and they're turning them into different things. Sometimes I'll have them make mobiles out of that block of foam, and this might be a way for them to integrate color theory or different design elements or design principles in that we might have learned about. And so like, you know, it's a sculpture challenge. There's requirements to communicate ideas like that or show things off like that in your project.
And that can be done. I mean, in art class, I mean, you have different avenues, which is nice.
Well, there's a gross one. And it's also a chance for them to think about materials and their properties, right? And I love that. What to do with a sock diversion thinking activity, where you try to come up with as many alternate uses for a sock as possible, right? And
Yeah.
it shows your divergent thinking capacity. And I like that. I really like that too, because like anytime you're going through in a design challenge, you have materials available. You're trying to understand the materials and what value is inherent in those materials that you could use for in some other application. You know, I think this is like, yeah, foam as an insulator. And sometimes I'll have to make something that has moving parts, or it's got to be a model for something. But just different examples up here. It usually has to be something that ends up being 3D. Sometimes I'll have them make like a desktop organizer for their bedroom, where they've got to make something that holds.
It's so crazy, all the different things that are made out of foam, like that they made and came up with.
Yeah. Yeah.
And you did this, what was this program with? Was it just your class?
Most of these are from, yeah, that creative design class.
Okay.
College students, anywhere from freshmen to seniors. And you'd think, wow, you know, I wish I had, you know, if I could do a project like that, not you, but some people look at it, it's like, oh, that's college level. It's like, well, these are kids who have never used a hot glue gun before. And I have students every year in these courses that ask for a demonstration on the hot glue gun. And if I don't give them one, they'll take the white Elmer's glue bottle with the orange tip and put it right in the back of the glue gun.
Oh my goodness.
And this happens because, like in New Jersey, I think, because of double blocks of math and language arts literacy.
Yeah.
Because right, for the last 10, for maybe not the last couple of years, but previous to that, with Common Core, that happened at the expense of science being cut back to like 1 hour a week in elementary schools across New Jersey. Right. And so you got to imagine so much of that got pulled out from students at one time, and now these kids are in college. So.
Yeah, because I mean, my middle schoolers were using glue sticks or hot glue guns. We were making cars completely out of pasta that had to actually roll and move.
Yeah. This one's cool. It has magnets behind it. And so you walk in when you're taking your earrings off, when you come back from
oh, that's awesome. Yeah.
Somewhere, and you just throw them at the sculpture and they stick to it.
That's amazing.
And if they don't, they fall back down to the bottom. Anyway, yeah, foam sculpture is cool. We're gonna move through some other stuff here a little more rapidly. Let's see. Here's a cool one. So I was working with a teacher who ended up taking this challenge for storm surge barriers. And these are actually hurricane-proof structures. The storm surge barriers are lower down here. She's a middle school librarian and makerspace person. The science people didn't quite want to do all the project-based parts, so she took them on her classroom. And when I met her, we developed this storm surge barrier activity where you make waves with this board here, right?
Yeah.
And the waves will come up onto the beach. And you've got to make a barrier that sits between the blue and the red line, right? And the barrier is supposed to stop water from getting into the house. And below the house here, there's actually a cup that sits underneath the clay. And that cup's going to collect water. Right.
Okay.
And so this, was like a climate change problem-based learning activity. And In this case, she had kids going around and buying materials for cost. You know, that was something they had factored into their final points, was, you know, how much money you spent on your supplies. And that doesn't always work out, right? That's a pain in the butt setting something like that up. But if you're trying to teach fractions and decimals, like, perfect, why not? You know what I mean?
Yeah, no, absolutely.
And see the sunset?
Yes.
All right, now this is the best part about a good design challenge. When the needs or the wants that create the problem are in conflict with one another or at odds. So in this challenge, there's people who want a storm surge barrier that's not going to stop them from seeing their sunset. That's why they bought the house.
Yeah.
Okay, so part of your point system, we call it a figure of merit. It's a way to add the points up to get a score as part of testing. Not that this is the summative assessment, but it's just the way we're assessing the testing part of the design process, right? Every step to us usually has is a chance to do some formative assessment, capture evidence of student whatever, so that we can use that capturing of evidence to show if they've met a standard, right? Because the evidence statements and next gen science standards are what tell us if we've met the standard. So this is cool because if you make a perfect barrier that's not going to let any water through, you're also not going to be able to see the sunset. And so you can't go too far designing toward one requirement without stopping yourself from meeting another requirement. And so this was
an awesome challenge for them too.
It was a lot of fun, and the materials were just like super simple things that they had to work with. And we made what I would call engineering notebooks. So they had a design brief that explained the problem. And of course, we didn't just read the problem to them. They spent about a week watching documentary footage from Hurricane Sandy and learning about how landforms change from climate and how all the different the science that goes into climate change and the climate's effect on the land on the earth, and also people's impact on nature is in those standards. And of course, if they had to learn sketching and drawing, which we did not teach them for this, but if they did, it would be something that we need to scaffold in, right?
Yeah.
At some point. And so here we go.
3, 2, 1. 1, 2, oh God. 3.
I know there's like how you gonna make sure that's the waves are the same for everybody, right?
Yeah.
Kids don't notice that.
This is so cool,
Kids,
guys.
they catch on to that, but we would do 10 waves or something like that.
It goes underneath the most.
And I love recording everything we do in slow motion too, because then I can go back and watch it in slow motion.
Right. Well, it's still.
And I can have kids predict how do you think your product's going to work, and make a claims evidence reasoning based hypothesis. And then you actually get to see how it works and how it performs, and you get to modify your explanation, right?
And you even heard the kid, like the one kid in the background was like, well, you can see the water's going under the house. So like even they're getting to observe it and see.
Yes, and that's awesome because that's where they get to make sense of it, right? So like,
exactly.
And so this goes right with, let's just take science by itself, but just like phenomena-based science, where you're going to be exposed to a phenomena, you're going to come up with an explanation. It's probably not going to be right, but then you're going to do something else, and you're going to come back and you have a chance to revise your explanation, right? Still there?
Yeah.
Oh, sorry. And so that coming back twice to revise your scientific explanation, you see that in a lot of standards, or that makes up a lot of many science standards, with that practice of identifying problems, explaining. So, but so that's kind of like how I see it happening naturally within the context of a design challenge. But that figure of merit was really cool. And so the engineering notebook, which would be like has a spot in it for what kids are going to capture at each step. I'll save you the trouble opening that thing up, but the point was that when it came down to the testing part, there were all these different numbers that got factored into their figure of merit. It wasn't just, did your bridge hold 20 pounds or not? You know what I mean? It wasn't that simple, not that straightforward.
Which is nice for them too, though, because like I like how you did the sunset. It gives them another way of like thinking, okay, if I was actually building a house, I mean, those are things you have to take into consideration when building by the beach.
Yeah, right. You didn't buy this house to block it with a big barrier you can't see through, but
Yeah.
that would be the best way to stop all the water. And this is also a shore town, so all these a lot of these kids have shore houses, but it's not that wealthy of a town where, like some shore towns, where they don't care about it. They have insurance for that reason. It's, you know, that's literally the attitude. But there was also safety lessons in here for hot glue guns, and we got kids little fingertip protectors, the silicone fingertip protectors to use for the hot glue. It's great, you know what I mean? Because there's schools that have stopped letting anybody have a hot glue gun because of getting burned with them, and that's just
Yeah.
ridiculous. And so you might take a hot glue gun safety test just like you would in welding. If you want to be a welder, you got to weld straight lines for real. I'll put straight lines and squiggly lines on the quiz, and you got to use your glue stick tip and trace over it with the glue stick without putting too much glue out or going off the line. You know what I mean?
No, that's awesome. How
I know,
long
and it's stuff. Yeah, this took 3 weeks.
Okay, that's it. Yeah, I was gonna ask, but it's awesome because it's tying in so many different standards, even though it wasn't the science teacher. I mean, the math, the science,
Yep.
the
And what do
English, everything all combined in there.
Yeah, and unfortunately, she's not the English teacher, right? But if the English teacher knew there was a deficit in something on language arts literacy scores on the state test that they got back in their data, they could say, "Hey, could you work on that skill in your design challenge?" Right?
Yeah.
Obviously.
No,
What
exactly.
do you now? I know you've heard the same thing from people when they first go, "Well, I don't have time for this," right?
Yep.
And you go, "I got to cover this stuff before they move on." And it's like, well, that's how you hold yourself that. But in reality, there's no money tied to that for your school, right? Funding is going to
No.
be tied to the testing. And so that's math, language, arts. This is your chance to change what you're doing. And
And in the
next
end,
gen,
you're actually finding that time is actually more beneficial, and they're getting everything that you wanted to have them learn, but in a better way for them to actually take it and apply it.
yeah, 100%. And so whenever a school wants to pilot activity, you know, or like take stuff on like this, I always recommend pilot. Let the people who really want to go forward and do it pilot it, and reward
Yep.
them by giving them more resources, more time, more space, right, for doing it. And then
And then let them
have
showcase it and say
Yes.
this is how it worked. These are things I need to change with it. But yeah, you definitely want people who are ready and willing to kind of take it on.
I
Because
got
it is
nothing for. Sorry, go ahead.
or I was going to say it's a little uncomfortable at first because, like you said, it does take longer than a day or one class. It's something that you have to be willing to commit time to.
Yeah. Yep. And absolutely awesome to see that happen and work out, you know. And I got to be honest with you, there's some over the 10 years, it's not like every district has invited me back, you know. For some
Okay.
people, so there's time. Well, I didn't know. And like in the beginning, everybody, a lot of schools in North Jersey wanted to get on this right away, and so
Yeah.
they went full bore, like in the really well, like Essex County, Bergen County, you know. And here we are 10 years later, and there's still school districts just starting to do this. But I
Okay.
guess like I was saying, it's kind of overwhelming, and if you don't have if there's resentment or people feel like this is too much, you know, they may feel like I wanted a STEM lab, but now that I have one, I got to be the one responsible for this space. And that
Yeah.
means that like you need to learn safety too, right? And
No,
so
exactly.
it could be a big undertaking. It's not just like a 2-day PD to come in and learn PBL. But 2 days is better than no days, that's for sure.
Yeah.
All right, so
Definitely.
I don't have any pictures here, but there's a fractals challenge for 7th grade. And the idea was you study fractals, what makes a fractal, what's not a fractal. And then if you can design your own fractal that has the elements of a fractal in it, right, then that's the design challenge. So that was
Okay.
just a simple one. That was
Yeah.
just for math. A name tag's a hokey thing, but it could be your first chance to get a design brief, right? Your first design
Yep.
brief ever. It's got requirements. It's got to do this, but there's constraints. That's what you're bound by or limited to during the design process, the inputs of technology, right? There's inputs, the 7 inputs. It's like tools, machines, time, money, information.
That one's awesome.
Raw materials.
That one reminds me of we did 3D pop-up books with my students in science, and they had to
Yeah.
construct and have so many different elements to it, but they had to actually research how were pop-up books made? How do you get the paper to do certain ways? How do you pull things out? And the kids at first were so apprehensive about it, but in the end, they turned out phenomenal.
Oh my God, I love that. And it's like it reminds me of how like anything you're going to take on where the technology they're going to be creating is something that's not really studied in class. Like if you're going to make a public service announcement that's supposed to raise awareness in your community. Well, the goal of the public service announcement is that you could show that it changed the community's awareness. So you're gonna have to put a survey out at the first step of the design process to even identify the problem or get a baseline. Oh, 40% of people didn't know what this was.
Yeah.
Okay, cool. Now, can we have a requirement that 80% of the people will know after they digest your public service announcement? Okay, cool. Great. Now that's the way we can test it. But you're going to have to like have kids understand what makes a good public service announcement at some point. That's something that they got to do at the research step, right? Just like you're saying, you got to learn pop-up books of paper engineering, and you would think, oh, well, that's an extra thing I got to teach. It's like, well, watch how much better it makes it.
Yeah, and it's still learning, and it's still learning standards that they need to have anyway.
Yeah, and I feel like project-based experiences, even if they don't look like they're connected to a standard, the point is they develop schema.
Yep.
And when I drive by a fountain and I see a fountain, I know what's going on with that fountain. I know there's a pump down there. I know there's electric runs. I know there's a flange that changes the shape of the water, all this stuff. When somebody else drives by a fountain, they might just drive by, go, look at that magical water machine, right? And so your ability to extract information out of any moment of your life, like how much you can derive from what you're looking at, is going to be based on your schema. And so to me, the more experiences with whatever it is, the better, because those are like branches on a tree that.
Absolutely.
I knew we'd be speaking the same language. There's a marble machine activity where each group has to make their own marble machine, like, marble machine. It makes a twist, it makes a turn, the stuff that he's like, this could be for like, in science, this could be for teaching forces or energy. And you may have to use friction to slow the marble down and make it get to a certain point by a certain time. And then everybody's got to link their different marble machines together and go down the steps.
Oh my God, that's awesome.
Yeah, huge waste of time. Or you think big chunk of time, but everybody gets to know each other and have fun in a low risk environment kind of thing. Done bubble investigations. I mean, when you can think PBL, you can think, well, you can have a culminating design challenge or culminating activity. And to me, that's just like saying, well, let's do all the inquiry first, and then I'm going to show you the problem. And now let's dive into the design challenge. I also look at it like, we'll just call the whole thing a design challenge. Introduce them to the problem first to wet their whistle, and then dive into the investigation, quote unquote.
No, right? I like that. That makes sense.
So here we are investigating bubbles and their properties, and then they had within there like little mini challenges as part of the research that make the biggest bubble, make a bubble that won't pop, make the most bubbles you can, and then they have to make a bubble machine. And so there's this rotating axle here, and these little things are spinning in and out of the bubbles. There's a fan back here. And so the test at the end was we were going to take a photo with all the bubble machines rolling, and we want to see how many bubbles you can count in your photograph when we take the photograph. Right.
That's so neat.
And then at the end for these kids, it was at the redesign, there was a big reflection about like how is bubbles as a technology, like how are like the things we learn about bubbles extrapolated into real technologies today? And there's some wild stuff out there.
How do you break when you say the redesign, like when do you struggle with teachers saying they don't have enough time to do that?
That's all anybody wants to say. And I gotta be like, hey, you gotta understand here, the redesign is my chance to show you as the teacher, I now understand what I was supposed to get because I made sense of it through watching all the testing and doing all the analysis of the testing.
Okay.
So if I tested my structure, my bridge, and we didn't just see who had the best load to weight ratio, but we recorded it and we played it in slow motion. And we tried to understand where the forces were moving through the structure when it broke. What did you hear? What did you see? Now, when you go back to your design and you get a chance to make changes to your designs that you'd make a stronger structure, all the little changes you'd want to make, you would reinforce with claims, evidence, and reasoning. Your new of how you better understand what's going on here. And so you should see those new decisions or changes in the redesign should show growth from where the students' ideas were at when they first developed the solution before they tested it, you know?
Yeah.
But to me, that's the whole point. Redesign is the chance for everyone to now build up their new knowledge of what was going on.
No,
So
absolutely.
in that idea of standards-based grading, you could find some kids will have get the standard before they do the testing. You know, if the standard was to explain that scientific phenomena, well, if they got the explanation, they met the standard. They didn't have to go through the testing to do it. But that's neither here nor there. It's paper engineering. Here's some pop-up stuff I did. When you said that, I got all excited.
Oh yeah.
I did it. I did this. There was a class of kids that would get pulled out of they were special ed and they were doing bad in standardized testing. And so instead of going to their tech class, they would go to an extra math class every day. And I was like, oh man, that's kind of boring.
Yeah.
Let's take the standards you messed up on in the standardized test and have you make pop-up books that explain those math practices or whatever it was.
That's amazing.
And structures like bridges or towers or cantilever arms that hang out like a boom arm and see how far it can go and hold weight still. You know, tower crushing. You talked about that earthquake-proof structure that you did. Was that with the shake table?
Table. Yep, exactly. We built shake tables for them.
Yep.
And they used toothpicks to build their whole hotel out of.
Oh man.
Yeah, we made it a little hard.
That's good. It should be a challenge. If it wasn't a challenge, they'd call it a design piece of cake.
Yeah, that's true. That's true.
And if everything we did was easy, we'd all be sissies when we grew up.
And they even had to do like a marketing for it because they had to do a whole presentation on their hotel and why they chose the way it looks. And they had to go to the design board, which was the teachers, and actually present their hotel to the design board for approval.
That's great. Anything to enhance or broaden what happens at testing or at testing. Yeah. So when you're presenting your stuff to people, you're testing it, right? You're gonna get feedback. You want to do CO2 cars and race? Don't just have who has the fastest car. Also do who has the most aerodynamic car with the least drag. Who has the car that is the best looking car? Who has the car? You know, give them multiple chances to be successful. Sorting devices. That's a very common thing in the technology education world. You know, where you have structures and mechanisms is something. A sorting device is a common activity you'll see out there. Whether it's taking beans and rice, and you got to dump beans and rice into one spot and have them spit out separate.
It's separating all that.
Right. This comes from the ag world, like 4-H clubs, and you know, they have designed challenges like this. You know, because that's a big thing in farming, separation. You know, you were in Arkansas. These were little storage devices. These were about just learning the design process. It wasn't to be covering content. This was in that intro to design course. So if you had to make so this was they required to make a containment device.
Yeah.
And so that could be a Pez dispenser, or that could be a locker. It could be a wallet. But it had to have compartments, and it had to have moving parts or features. And you'll notice too, like every technology, this is why you got to learn technology, like some of the nature of technology stuff with design thinking before you move forward, because you'll learn like, oh, every technology has not just function, but it also has form.
Yeah.
Right? So you can have requirements for the way it works, but also how it looks and what its affect is. And so that's something that we overlooked a lot in a challenge. It's like, you know, we could beef up these requirements. We have a lot of requirements here for like how it's going to work. Because you ever have them think about how it's going to look too? And
no, it's another way of them thinking.
Recycled footwear stuff. Making a hanger to hang up your TSA uniform. TSA is Technology Student Association.
Okay.
It's the career technical student organization that goes with the STEM cluster in the CTE career technical world. If you're in the agriculture cluster, your club is the 4-H club. If you're in the
Okay.
business, if you're in the business cluster, your club is the DECA. Did you ever hear that?
I don't think so.
Yeah, Midwest is where a lot of the career tech stuff's much bigger than it is out here. But
Okay.
TSA Club, they have 60 design challenges you can compete in high school and 30 in middle school. They have state competitions and state agency, and then they have a national competition. But one of their intro challenges is, can you design a hanger that hangs up your TSA uniform? I love Play-Doh.
Yes.
I just started working with Play-Doh is like chemistry, and there's a really nice elementary unit from Engineering is Elementary. You know EIE?
Yeah.
Yeah, so big National Science Foundation project that's started back in the early 90s. Integrative stuff, follows the design process. In every EIE unit, of which I think there are 20 for K-5, they basically focus on just turning science into a science paired with engineering. But now they go further to more integrative STEM, where they have also math
That's
calculations
awesome.
that have to be performed before you finish. So the way that their design process work, in the ask step, everybody reads a storybook, and in that storybook,
Okay.
there's some group of people out there that have a problem that you want to help them. And in the storybook, you're also exposed to real science, right? And so that's how they're identifying the problem. And then they start doing brains. Then they do, as also part of ask, they do an experiment next, right? So those experiments happen before you go into now brainstorm, make something, and then test it. But what I was doing recently with this class was a group of special ed students. I think you call it SDL. Is that severe?
Okay.
Or SLD, severe learning disabilities?
Yeah. Yeah. SLD, I believe.
Yeah. And so like I was in this class, and you'd come in the morning, and they would like, the kids, we would be like, one kid has to go up and tell everybody what the weather's like today and what the date is. And I was like, wow, this seems like, I just never was aware of like what's going on in that classroom,
Yeah.
And then for these kids, tactile stuff was so cool, making the Play-Doh. And then of course you have some autistic students that don't want to touch the stuff.
No, it's true.
But the idea in this unit was, you're a chemical engineer, and you're going to come up with new formulations for Play-Doh, and then you're going to model new playground structures. So for this, it was the problem. We went out to the school's playground, and we came up with things we want to change about the playground, problems or issues with the playground, and then modeling structures with that. Here's a wind turbine, or stuff with wind. There's another EIE unit. This was second grade, and in part of their investigation, so they had to make a wind turbine. So they have to make little blades, and the blades are going to spin when they get hit by air, and it's going to work like a windmill that not to generate energy, but to crank up a little cup full of paper clips or something. But for the investigation, they had to make sails. And so you would make different sails and hook them up to this thing. And then we put them in front of the fan, and they would let go. And they, like, how do you think it's going to move based on the shape, and then they refine their explanation. And we do these like little mini races. And absolutely love that. It was funny because I'd never done it, and I got all intimidated myself. Like, I build stuff every day, and I was like intimidated, like, oh my God, how do you make a zip line? How do you make a zip line?
Some good fishing line.
yeah, it's a good fishing line.
That's what I learned.
Let's see if I got one here in slow motion, because that's the idea too. Like, a slow motion video gives us a chance to watch the slow motion video, and part of the analysis of testing or the evaluation is you never see like John Madden in football. I don't watch football, but I remember that guy in the 80s. He would draw with a pen on the screen.
Yes.
And show like what the players did. I think that's what you need to do when you play back your slow motion footage, is go up to the smart board with a pen and go over the video and hit pause and be like, here's where forces are moving. Here's where I think this is happening.
No, it's amazing.
All right,
it draws
raceway
right
fans,
to them.
are we ready?
Sorry.
Clear the track. Clear the track.
Are you ready to rumble?
Let's get ready.
So loud.
To rumble. In 3, 2. Do not push it. Let go of it. 1.
There were kids who would throw it.
Oh my God, that's so true though. Like, yeah, you do have to tell them that.
You know, and like watch that kid's face. You show that clip on back to school
Yep.
night, and the parent is excited during your class.
Well, the best is the kids remember these things. Like you go to them those are the things that they remember from their classes and what they learn.
Yeah, my dad used to tell me growing up, Chris, you're not gonna be rich when you grow up because you're in teaching, but it's a noble profession. Nobody remembers the name of their banker or their accountant when they're 70 years old. You know what I mean? But people will be telling stories to their grandkids about you as their teacher
Yeah,
back in 3rd grade for the rest of their life.
it's true.
This is a Rube Goldberg devices. You know, it was like, you know, the Rube Goldberg, it's a common thing. How do we stretch out a simple thing and make it go on forever? But when I was thinking about simple machines, it's like, you know, this one, it was like, how many simple machines can you demonstrate at one time in here, you know? And this could be like, could you make the whole thing happen in a certain amount of time? Or I don't love Rube Goldberg because it's kind of devoid of like a real world problem.
No, like connecting it to, yeah.
Yeah, but it's a fantastic way to integrate a lot of different things into one activity. Any events.
No, these are awesome, but I'm gonna head off just so I can get some other stuff done. But thank you for letting me join and kind of see some of the things that you've done. They're awesome, amazing.
All right, I'll send you a copy of the video when I'm done. I really appreciate your time. And this
No problem.
This got me so pumped up today talking to you. Thanks, Brielle.
No problem. All right, talk to you soon.
All right, have a great day.
You
Bye-bye.
too.
See you later. All right, so back here talking to myself. No big deal. These are air-powered rockets. Take a 2-liter soda bottle and you put fins on it and a cone, and it hooks up to this little device that costs $30. You pump, 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 pump.
Ready, Joe? Walk it backwards. Yeah, walk backwards. Keep going. Pull. 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 Yank it. Almost. Almost. Harder. Harder. Pull. Pull. Woo! Yeah!
Looks like I got to lose a little weight. Okay, maglev. So we've seen a magnetic track before. There's a picture of the track. You can see the magnet strips, and these tracks have aluminum rails on the side, and you know the aluminum will conduct electricity, which is cool because in a lot of places where I've ever seen the maglev being used, it's like you know, you make a little vehicle that has magnets at the bottom of the vehicle. You can see the magnets right here, right? And those magnets are going to repel and make the vehicle hover. And people will maybe study aerodynamics and have kids make blocks with different shapes and then put this maglev track up on an angle, like so it's a gravity fed thing, and see how fast you can get it to go down to the bottom by reducing the drag. But you can also take a device and charge the track up with a little AC/DC converter here. So it plugs in, and then you put a positive on the track and a negative to the track. And now that the track itself is charged, you can take a something like this device, which has the motor on it and the battery pack. Take the battery pack off, right? And we could put the leads that run to the battery and just have the leads hang out and brush against the side of the rail, kind of like the way a trolley car would run back in the 50s, right? So and this one was a control systems challenge where you had to not just create the device to propel the car forward, but you had to create some type of a control system. Here's a switch, and what's going to happen is as it goes down the track, there's this crossbar here, and so you have to make your design of a control system such that when the car goes below the pole, it will automatically shut the car off so that the car doesn't make it to the very end of the track. And that's one application of maglev. But another application, oh, that's pretty cool. Doesn't help if you don't make it all the way. But an even more fun application of maglev is egg crashing vehicles. And so in this challenge, every student makes a vehicle, and the vehicle will be launched with CO2. All right, so that's a little starting block that punctures the back of a CO2 cartridge, which sits inside the block here. And
Now, did it move up or down? Like, can the car move in and out smoothly now? Right back into there? Yeah. Okay.
so the way this challenge works is this obviously was used for forces and science, and everyone builds the same chassis to start with. All right, so so this activity was used to introduce students to the makerspace and to run a safety unit that would expose them to the basic tools and machines they'd be allowed to use during that year. And the chassis itself could be made of cardboard or Luan plywood or something thin and light. And whether I make the chassis with the kids or I provide the chassis, it depends on what we're trying to, how much time we have. But you've got this 10-inch block, and then you have a foam block glued on top of it, and then your magnets underneath. And really got to get the magnets just right and the width of the block of wood just right, or else it'll flip out of the track. But every student makes this called the chassis, like the base. Now from this base, you now have to create a system on top of this that's going to contain an egg. Not just contain the egg, but it's also going to allow you to take the egg in and out easily, meaning I can't wrap this whole thing up in duct tape. I can't put anything underneath the vehicle that would slow it down. And I'm going to be given constraints for how long I could make the vehicle conceivably, how much it could weigh without going over. And and other constraints, like nothing goes underneath the vehicle. And so once the vehicle crashes, the teacher has to be able to go in and take the egg out immediately and inspect it. And that's why you have to have some mechanical device for storing and then retrieving the egg, and some device to like keep it contained in there, whether it's a seat belt or a latch or something to hold on to it. And so there's CO2 race cars that race on just on the floor or across a zip line. But I thought, wouldn't it be cool if we could do the same thing with the CO2, but over maglev, because there'd be less friction, right? And they'd probably go really fast. And they do. And so students are designing their, as part of going through their engineering notebooks, and they're designing lots of ideas for the vehicle, and they're predicting how they think it's going to work. In this case, we made this whole challenge. I mean, look at this. Here's a bunch of the tracks put together. We said, hey, everybody gets together to come watch the school's basketball games. Can we get them all together to watch a STEM event? And so we videotaped the track and put the video up here on the big screen for the audience to watch back in the stands. And we have a starting gate and a finish gate from a CO2 track that allows us to time the vehicle, so we know how long it took them to go from the beginning to the brick wall. We either crash them into a brick wall, or we crash them into each other and head-on collisions. And after each time it crashes, if the egg has survived, you go into the next crash with a beat up car. Or after the crash, if your egg breaks, you get a chance to go over to the pit stop area, where you have to write an analysis of why you think your vehicle failed. And then you come up with a new design very quickly and fix your vehicle in the pit. And then you get to come back out for another test. So this is more of an iterative testing thing. We're just redesign, test over and over again. Can't weigh more than a half pound, or else the vehicle will not really travel, will not go fast enough. And let's find a nice slow motion crash here for you to see.
3, 2, 1.
There were also things in here
Man,
for
it broke in half.
That's sick.
how tall the
That's
vehicle
up.
could be, how wide,
That is sick. That's the first.
and again, playing these back in slow motion, then having students explain what they're seeing as part of the analysis or testing and evaluation. And super fun activity. This took 3 weeks of class time, could even take 4 weeks, but acclimates everybody to the makerspace, to the tools and machines. This was so cool. This is an egg suspended in here that's hanging from these rubber bands. It's not touching anything. And the idea here is that this is going to absorb the force of the crash in the rubber bands, because the egg, when it hits, is going to bounce back and forth. And again, when they're told that it's not, if the egg breaks, that's not your grade. That's just part of the factor of the assessment along the way. Because we want kids to take risks and make mistakes and be okay with failing. And so you want to have wild ideas, and that being ambitious like that should even be rewarded. Here we go. Let's hear this. Cool. All right, so that was maglev. There's some balloon-powered vehicles. That's an activity's been around a long time. All right, so you've ever heard of a Mousetrap Car? You get a little kit you buy, and it's got CDs for wheels and a mousetrap. And the idea is that when the mousetrap is hooked up to a back axle with a string, you can roll up the back axle, and when you let it go, the trap won't slap real quick. It'll slowly unwind the axle and make the car go. Well, that's a common thing with a kit. So when you put a kit together, you're not designing, right? You're just following instructions. But making a Mousetrap Car kit as part of a Mousetrap boat conversion activity, well, here they're gonna have to make a boat that's gonna travel through a track. So I set this plywood thing up and put some liner in. I built this thing in 15 minutes, but right before parents showed up. And at the research step of the design process, they all made the Mousetrap Car, but then from there on, they had to redesign so that it would be a vehicle that floats on water. And here you could be going for the fastest vehicle, something with the most speed, or the most powerful vehicle, the one with the fastest car with the most torque. And then the fastest boat, and then also the boat that can go the greatest distance, right? And so you could design for one or the other, but not both. And we had boats that went back and forth in this 20-foot track, and we kept having to turn them around. And we wanted boat went back and forth 10 times before that mousetrap slapped all the way down. So you can see the trap here actually has an extended arm that goes up and then attaches a string down here to the axle. And so they were trying to make these things buoyant and propel, but just fun trying to put it together. And the water was great. Found it was nice too if the boat tracks in there for a while, to put a little chlorine in the water, a little bleach, because everybody's sticking their hands back and forth in there. This was an independent project where a student took GoPro cameras up into the stratosphere, and they basically had a cooler attached to a giant balloon, and they would let it go, and it went so high up until the pressure of space pops the balloon, and then the thing was filled up with different GPS devices and all kinds of stuff. We had to tell the FAA that we were going to be flying this thing up into the air, and then you have to go and try to retrieve it when it comes down. And it's not documented, but this was in 2008, I think. No, it's 2012. And one of my buddies helped one of my seniors with this independent senior design project. And I don't know for sure, but I think they were some of the first, it might have been the first kid under 18 to launch something like that up into space. It got real popular a couple years later. I don't have the video of it happening here, but super cool. All right, ooh, cultural systems, logos, screen printing, color theory. You know, color can be part of a solution. Color is emotion, or color for aesthetic. And so we learned color theory, but we did it on, instead of using watercolors, we used cake icing that's white and food coloring. And so they would make the primary colors in the color wheel, and then make secondary colors, and then take one color and make a tint or a hue, or take one hue and tint it, making it darker or lighter. Edible color theory. Let's look at some power, a couple power energy things. These are LED lights. This is cool. You know, LEDs, when you're teaching electricity and circuits, you learn soldering or breadboards, there's resistors you got to put in there and stuff. And what I found is that if I took holiday lights, and let's see, here's the picture. It's like a string of Christmas lights, right? These LED lights or the incandescents, doesn't matter. And you chop these things up and separate them into individual LEDs. You can wire them in parallel, meaning stacking them on top of each other instead of one light to the next in series. In series, you cannot light up more than one LED with a pack of AA batteries. But in parallel, you can light up 30 of these LEDs like this. And so this is a simple circuit. It's got a switch, it's method of control, it's got the power, it's got the resistance here. And these you don't have to wire in any little resistors. You don't even have to solder. And so learning to make a circuit like this and learn how electricity works and how to control it is a great core investigation where you create something at the end, a model here, but then using this to solve a problem, any number of design challenges can be wrapped around that, because students created a signaling device to send messages with light, or you can use the light to illuminate things, obviously. And so sometimes students are tasked to find their own problem where light can be part of the solution. Where emergency flashlights, apocalypse flashlights, recycled, repurposed material lights. Right, these two folks are the runners. This would keep them more visible in the dark. The students were tasked to try to amplify the light or reflect the light waves. You know, when you're teaching waves, we could do it with light or sound or liquids, fluids. This could be used for something like that as well. And don't get me wrong, soldering and circuits and all that stuff is cool, but to me, this gives you a much better background than something like tiny bits or little bits or whatever they call them, because you actually have to manipulate the stuff to make it work. It's not just plug and play. And it's in that little bit of troubleshooting and putting things together that you learn to be more persistent and patient. You know, this was cool. This task, we taught this to older kids in high school, and then we had the high school kids introduce a Lady Gaga dance-off competition. Lady Gaga was much more popular at the time. This was a while ago. And so the students had to use the lights to make costumes and then coordinate some type of dance routine where the lights were part of the routine. And we even had some kids that had contacts on their hands made of tinfoil, and when they would grab another student's hand, it would make the connection and the circuit would light up. Pretty cool. Let's see if we can hear the music here. All right, just that right there, I'll get me flagged from YouTube, I'm sure. And in many cases, when I'm using this activity, I've done it outside of science class, where it's just a way to introduce the tools and machines and the design process. night lights. By the way, foam core is a remarkable material, you know, for presentation board. You could cut splines in it and make them into cylinders that don't crinkle up. And there's other cutting tools for cutting lap joints and rabbet edges or dado slots out of the foam core. Really remarkable as a structures material. Signaling device for students that want to, that's what this person focused on. I need help, green, yellow, red. Or a night light that helps a child who's afraid to go to the bathroom in the dark. You know, you'd have to interview that child and get to know the problem, of empathy for them, so that you'd be able to come up with your own design brief of based on the person's needs and wants. She said her husband goes running in the dark and she's always afraid he's going to get hit by a car and he won't wear the reflective vest. So she says, "What will you wear?" He said, "Anything with Batman." So here's a Batman safety light. Anyway, one of the crazier challenges I've done with this, that was, you know, more deep design challenge, was that you were going to be going to Mars and you needed a signaling device that would allow you to be on the surface of Mars and still shoot light information to people in case there's an electrical storm and everything gets knocked out on the surface, which happens apparently on Mars. These electrical storms, you still have to be able to communicate. But you're also going to need to use this light as a night light for reading when you're in your little pod in the structure that you live in on Mars, because you can't take, when you go to space, everything's got to serve multiple purposes. You can't just load up all the cargo. It costs $10,000 per square foot for stuff you want to send up there. So things have to have lots of applications. So how do you make a light that's strong enough and powerful enough to send bright light signals to people on the surface of Mars in a dust storm or electrical storm, as well as a quiet reading light that you can use to light up your book when you're reading without disturbing the person who's in the pod right next to you? And so having to be able to do both of those things is what we introduced in this challenge. And I remember the hook at the beginning was a podcast where Neil deGrasse Tyson is arguing with Bill Nye the Science Guy about what it's like on the surface of Mars. And you get the kids are frustrated in this contentious debate between these two science leaders. And it raises all these different questions and issues, who's right, who's not. And it was just a nice way to enter in, because the kids recognized Bill Nye. And so these were some examples of devices that would do both. Could be a signaling device on the surface, but also be a quiet reading light. So how was this great? Let's take a look at some of these things here. Oh, they also had to make their own switch.
Whoa, yeah, gluing the magnets to the right side and getting them to stick together correctly. Very cool. And what would you say the most?
Need to hide the battery pack. A couple other requirements in there.
Why is aluminum foil a good replacement?
You had to be able to get in and out to change the batteries. That was another requirement.
Make light when you touch it with the metal.
It means it's a
Conductor.
Exactly, perfect. I love it. So really quickly before I
Just want to find this one here that shows how the student made the light brighter and dimmer without a potentiometer or anything like that. And let's see somewhere. Here it is. Check this out. So the light also had to have some sentimental value and remind you of home, so you didn't feel so lonely out there in space. And so that was another requirement to incorporate into it. So for this child, it was the cat.
So that like the light wouldn't just like show through, it would look more like glass or something. And this part, you can like take it and make it a flashlight. And I used a push pin switch. Also the battery, you can take it in and out by taking out this paper clip and opening it, and the battery is inside.
These are 5th graders who had never been in the makerspace before, their first forte into larger problem-based PBL.
Yeah.
So right there you have your handheld flashlight for when you're outside the habitat working on Mars, and then you put the cat's head back on.
And I have a reading lamp.
And it functions as a reading lamp, a discrete reading lamp.
Boom, remarkable. And it's funny is when I start the challenge, I've never done this before. I go, man, I don't know if kids are gonna be able to pull this off. And then it's like, oh yeah, no problem. And so I try not to let my own biases or what I think may or may not be able to work get in the way of me trying something out for the first time. You only know when you try. But kids often don't see the same problems that in the way when it comes to creating something that you would as an adult, because you see what you see is a culmination of all any bad experiences you've ever had that might intimidate you into thinking something's not possible. But for kids, they don't have any of those as many of those fears or concerns, and so they'll give it a shot. What I wanted to say back about this wind power thing here was where was it? Wind power. Where'd it go? Well, the point was that in the wind power turbines, in one activity, the kids were designing blades to make a more efficient wind turbine, but it was also the idea that you also had to have another component to your design, which was how is your wind turbine going to stop killing off all the owls and birds that are getting killed yet? And also, how do you make a wind turbine that blends in with the beautiful scenery out there in Appalachia that's drawing people into this tourist industry now in a once completely economically depressed area after coal mining left, right? And it's like, well, how do you make a wind turbine that does all these things, stops the birds from being killed, is not unsightly, but also generates electricity? And so, for part of that design, we couldn't actually bring birds into the room and test a full-size wind turbine to see if it actually your solution kept the birds from being killed. But you could pitch your idea for a solution, back it with claims, evidence, and reasoning, and then give students in class a chance to respond to you and poke holes in your theory and debate the merits of your design. And so in that wind turbine thing, some kids were given articles about how coyote urine as a pheromone can repel, keep birds away. And so a student used that as part of their claims, evidence, reasoning. If they could maybe make a paint to paint the wind turbine with that had coyote pheromones in it, and that would keep the birds away. And again, I'm not bringing coyote urine or birds in my room, but if I have more than one requirement that you have to meet, and there's requirements fly in the face of various people's needs and wants, you got a perfect challenge. Okay, let's see here. Oh man, horseshoe crabs, this was cool. You get a big tank and we get a chiller that keeps the water cool. You're in salt water and the kids get to watch the horseshoe crabs grow. And then designing a habitat for them. And hydroponics, aquaponics are some of my favorite areas. So this is my old classroom. I had a 1,000-gallon livestock tank in the room. We filled it up with water and fish, and then this was used to distribute water to different hydroponics or aquaponic systems with the water.
Time for an update. Last time I posted a video, you could see the plants were pretty small. At this point, the fish tank water is still really clean. There's Carl and Chow Ming. Sorry about all the reflection. Grow lights are pretty bright. They cause quite a glare, but I have over 100 different plants right now. This is thyme. The day before, they'd never been frozen, they were fresh. We cooked them up with some butter, red onions, and
but having that in the room was like a big demonstration piece and a learning tool. And science classes would come in and do experiments with the water. Kids liked having the running water in the classroom. It was, calming, soothing. It's that biophilia effect, bringing nature indoors, known to reduce cortisol levels and stress. But the hydroponics design challenge was like the basic one for biotech that we would start with. And here they're learning about how farming is a technology, making plants grow where you want them to grow. That's technology. But there's also, like any technology, has benefits and trade-offs. There's problems with farming outside. There's a storm or a frost wipes out all your crops, kind of thing. So how can you recreate all those variables indoors and grow a plant without any soil? And so in this challenge, everyone makes some base model together. And the base model consists of a 2-liter soda bottle with a top cut off and flipped upside down, turned into a cup. And then inside this cup is some inert medium. Here we have hydrocorals, but something that takes the place of soil, but it also doesn't add or take away from the water composition, and is light and porous and gives the plants a place to grow. In here, there's a little cube of rock wool with a plant growing out of it, just like you buy the basil at the grocery store. Forget the pump here, this pump, take that out. Everybody just starts with a 2-liter soda bottle of cup. And your job is to do a bunch of investigations in stations or centers at the research step, where you're gonna have to investigate different requirements for this challenge. So by itself, this hydroponic thing sitting in a window is going to help grow the plant through capillary action. Water travels up this wick. There's a t-shirt strips here tied from the bottom up. And if this just sits in a window, there's going to be problems with it, right? The sunlight is going to be amplified through the plastic. It's going to heat the water up, and warm water does not carry oxygen and does not good for plants. Water that just sits there and doesn't move also gets stagnant, and so the nutrients in your water are going to start to grow mold. And another thing is, if they're sitting in the sunlight, you're going to get algae in that bottle, right? And so how do you create subsystems around this structure where you can agitate the water, deliver water up through a wick? They'll investigate, do a lab on capillary action, try different wicking materials out. And they have to reflect the sunlight back onto the plant and capture as much sunlight as possible. They have to keep this thing from tipping over. So it starts to get top heavy. But I've grown one cucumber plant out of a 2-liter soda bottle where it sucked up a liter of water every day, and the cucumber plant was 20 feet long going down the sidewalk. And so there's a lot of different requirements, and each requirement in the challenge is the invitation for the teacher to create some investigation or inquiry experience at the research step, so that students can take what they learn from that and apply it to a solution. And this too is not like testing the solution you come up with is not like crushing a bridge where you just get all the data right there. We test these by putting these in the window once they're done, and every day collecting data on the temperature of the water, how many new leaves are grown, weigh the thing compared to what its weight last time, stuff like that. And so for that, testing is a process that occurs over the course of a month. But students are learning to use different scientific instrumentation as part of this. And we start the plants in these little rock wool cubes, these little cubes made of volcanic rock and shale, spun into fibers like cotton candies made of rock sugar. And the plants start out of here, and we pull the cubes out, and the cube goes into the system. Let's see here. All right, so here's some systems. So we had students design these for a nursing home, or design them for some other specific purpose. They had to both have form and function and form, right? So here's a pump with a bottle and a little hole in it. You put your finger with a little squeeze of the bottle. It's going to blow bubbles into here and agitate the water. In the redesign, we might say, well, how could you make that more efficient? Oh, you could make this longer and run the tube, put the bottle on the ground so you can step on it with your foot. That way you can pump air with your foot so your hands are free. Just keep challenging kids to optimize, make these things more efficient, improve the design somehow. And you had to keep the water covered up so that it would grow algae. They also have a way to test the water to find out what the water level was, even though you can't see it. And some of these things are just like remarkable. This was a tube that you could put a dipstick in, and the dipstick had little measurements on the side of it. And so you could stick the stick in and see where the water level was on the stick, and that's how you know how high the water was. Then extending this out and taking aquariums, and instead of putting nutrients in the water, you use the fish waste, right? The NH4 ammonia gets broken into NO2 and NO3 minus nitrate and nitrate, which get absorbed by the plants. So the plants are filtering out the water for the fish, and the fish are feeding the plants with their waste. And water gets pumped up to the end of the gutter, and it flows down the gutter and falls back in. So everybody's got a fish tank. Every other person on your block has an old fish tank defunct laying in the garage, an old fish tank filter, gravel, you know, stuff like that. So we took a little cart that was used for TV/AV, and we put a little light up over the top and hooked everything up to the back with the timers. Show you another. I remember we wrote a grant for hydroponics with a teacher, and it was about, you know, the grants application are all about showing impact, how much bang you get for your buck. It was like, well, we're gonna have the students do these study these hydroponic systems in class, and then we're gonna model a bunch of different types of hydroponic and aquaponic systems, whether it's with a wick or with a flood and drain, or with misting the water or gravity fed. But then the idea was that once the students made these systems, the students were going to teach workshops to younger kids and adults in the community, and then that would replicate out and you know, put an exponential factor on the impact over time from that one activity. And so here's a bunch of student solutions on the table under a grow light, and they're finished. There's a flood and drain table where water floods the tray, and then 5 minutes later it all drains out. So the plants just get wet a few times a day. There's a geodesic dome, which is freaking crazy. And this was at a school in
Geodesic Dome.
Holland, New Jersey. Like a whole new world when you step in there. Here we got the fish tank.
This came with it.
Yeah. Well, actually, you had to build this. It came with a liner, and we had to get the metal.
It's still pretty cool. I thought it'd be hot. It's not.
So the way, I'll let you know the video.
Okay.
You know, she was yielding like a case of vegetables out of here every week, if not more. And so cool. You know, I had a student one time who kept getting caught selling pot, and this was years ago. And I said, you know, what are you doing this for? You're really making that much money? And he said, yeah, I make a lot of money. And I said, well, I bet you we can make more money. I can make more money in a couple of weeks with tomato plants than we could make selling marijuana. And so what we did was, you know, these grow trays, right, with these cubes in them. You get 98 plants in one tray, one starter tray, right? There's different media. And so we stayed after school one day, we propagated 10 trays, planted the seeds. So we had 1,000 plants basically sitting there on the table. It took us 30 minutes to put the seeds in and add the water, and then put the dome on top. And then we just let these things sit there and kept them moist under the light for a couple weeks without having to do any work. And once the plants were 4 or 5 inches tall, we invited a couple kids down to the classroom. We took the plants out and put these little cubes into a soil cup. And that took us about 2 hours, right, to do 1,000 plants. And they're 6 inches tall. And then we marketed pretty hard about 3 weeks early, where we knew parents are going to be coming in for different events with sports. And we said, hey, during Mother's Day, everybody goes to Home Depot to pick up your tomato plants for your porch or your garden, your tomatoes and peppers. Come buy them from us for $5 a pop instead of 10 at the store. We're even going to have them outside lined up, waiting when you pick your kids up. You can grab them. You can even pre-order them. And we didn't sell all 1,000 of them, but we did sell like 700 in a couple of days. And we ended up with 700 times $5 a piece, 3,500 bucks. And it cost us $200 in materials and 6 hours of time. And so, you know, convenient, we get parents to buy the stuff. It's not the same as just starting a business out there fresh. But the point was, we made way more money in a short period of time and demonstrated it as part of a club or a community activity. And we raised money. We could get back to the department, or let the kids have a kitty where they could raise money and use that money at their discretion if they're doing what they're supposed to be doing with the club otherwise. And In the end, it turned out the kid kept selling pot, and it was not about the money; it was about status. So I need to come up with another way to address that. Some elementary stuff. So working in a teacher's classroom in a school district where the math, they were having trouble with certain math standards, and they really need to show improvement in that. So they took their best math teacher and put her in charge of the tech class, or the tech cycle or special that every student has to go through. And they're going to learn coding in the tech class. But they're also going to use these tech design challenges, not just to learn coding, but also to reinforce areas where they were shown weakness on their testing in, like I said, math and language arts literacy. And so there's these Ozbots, just these little robots that you learn to code, and they're different than any other coding platform. But what the kids had to do is make a little character that is wrapped around with paper. It's a halo that sits on the bot. And the kids got these storybooks that are just picture books with no words. And their job was to write out the story they thought would go with the words and the pictures, and then program their robot to travel around from one page to the next. So there's a 10-page storybook. Your poster board would reenact the 10 pages in the story, and your character has to be programmed to move like the people in the story. So if they're running up the steps in the story on one page, your creature, your robot needs to go like boom, 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 boom. Let's go up the steps. If it's running a straight line in the next story, then it just needs to move in a straight line without any pauses. If in the next picture they're standing for somewhere and then they move to another part of the room and then come back, that's what we need the robot to do there. And so you're writing the story that goes along with it and learning to program at the same time. And the students are none the wiser that they're getting better at the stuff we want them to for the next year when they take those tests. And that's the way to do it, right? You don't want to take those kids who are struggling and pull them out and put them through an extra math class where everybody else gets to go to the fun tech class so that they can do test prep. We also use the Ozbots and made little shovels that you put on the front, or a scoop that you attach to the front. And they had a challenge to try to move snow around without hitting the parked cars and without bumping into any of the landforms. And this was a real problem in their town where when it snowed, it's like people had never been driven in the snow before, and the snow collection was a big problem with traffic. And so they heard their parents talking about this, complaining about it that every day. What a great way to contextualize a real world problem that's relevant to students' lives. A lot of gardening, composting with kindergartners, making a community garden, and then selling the stuff at an event somewhere. Pet bath design challenge that's from an EBD teams unit, but again, kind of like EIE, there's a big storybook, and in the end, you're tasked to conserve water. Make a device that will let you give a pet a bath without and conserve water at the same time. And so kids are making different devices that would model on a scale, being able to conserve water, giving your pet a bath. Love this one, treehouse challenge. A tree is a fractal. So you pull a branch off, it kind of looks like the whole tree. Students read a book about a kid whose house keeps getting power keeps getting knocked out from storms, and this creates a problem for the kid. So the kid wants to build an off the grid treehouse. And in with the treehouse, there's requirements for like being able to get in and out, or compartments for this, that, but also I'd have a light in it that's powered by a solar panel. So they reverse engineered the solar walkway lights and pulled the top off with the panel. And then we just reran the back, reassembled it, the guts of it inside so that it would light up at night. Now, where this solar panel gets placed, right here, this one's flat, but in this challenge, the students do investigations. And so everything they're required to do with the treehouse later is based on an investigation previously. So the students get a solar panel and they get a little protractor for measuring angles. And it's their first time collecting data and putting it onto a chart. And so in the experiment, they have to hold the light on different angles, 15-degree angle, 30-degree angle towards the light source, and hook it up to a voltmeter and see which angle actually gets them the most electricity. So that when they have to pick where the panel is going to go on their treehouse, which direction it's going to face and on what angle, they do it based upon what they learned in the investigation. Super cool. you know, and it's just a stick come off from the tree outside, glued into a block. And this is nothing. I don't have any pictures of like really good ones. This was just something we threw together to do the workshop. But there's another EI unit in elementary where the kids read a book about how there's less bees and not enough pollination going on. And so in the experiments, students are going to be tasked to make a device that would allow them to hand pollinate flowers in place of the bees. And so we replace pollen with baking soda, and we do all these experiments with how different materials can help collect pollen or drop pollen, and then shaping your different tools that could fit inside different types of flowers that are shaped different ways. And in the end, we actually have model flowers, and the kids go around and try to pollinate the flowers, and we go into the model of the flower and see how much pollen they were able to collect inside. You know. There's them taking the cotton balls and erase different stuff, dipping them in pollen and touching the paper to see how much pollen sticks and how much doesn't. And in the end, they have some of their tools that they end up creating. And so here they're doing their language arts and their social studies and SEL involved in the problem that's going on. And then there's investigations and then the design, all captured in the student's engineering notebook. Students have to learn to label and organize their papers, date, align things, use proper handwriting, spelling. All those are skills they got to do anyway, but instead of doing them separate, they do them as part of this design challenge and collapse or fold or subsume those skills into the activity. All right, let's see what else we got. Well, we're going for a while here. It's a long one. You asked for it. You're going to get it. I'm excited to share these with you again. I'm sorry it took me a while to put this together for you. Oh, some other activities. See some stuff we did with our laser cutter. Of course, we engraved lots of things with it, and then we started getting more into the cutting parts and then figuring out what else, what are some other cool applications for this. And so I found out there were paints called sear mark paints that you could spray the paint onto metal, and the laser will photochemically bond the paint to the surface of the metal. And then you just take the thing out, and anywhere the paint did get with a laser, you wipe it off with water. And that's a way to mark metal. And when you can also get paints that you can mark ceramics with, whether it's glass, and even wood. I remember we took the live trace tool, and we would take a graphic, and then we would live trace it, and then we would turn the graphic into a high contrast image where it was either black or white. And then we would cut that image out with the laser cutter and make a stencil. And then you hold the stencil up and spray paint through the stencil, and you get this image here. Right, there's cutting out a stencil. Here's cutting out a piece of acrylic, cast acrylic or plexiglass, and then we put little LEDs in a strip right up to the edge, and light shoots through these things just like fiber optics work. And anywhere that the plastic has been etched or engraved, it's scratched, it's going to diffract the light and pick up the light and blast it. These are exhibits, point of purchase displays to sell a product. We had a little laser cutter, and instead of buying a $4,000 HEPA filter from the company, we built our own, filled these up with charcoal and a filter here, and the air would draw through this and keep the fumes, allow you to run your laser cutter inside the building. This is from mini golf. We wanted to make mini golf course, a mini golf game. That was so everybody would design a mini golf course hole, and it would be a fundraiser. And you come to the fundraiser and you play each hole, and it would cost money to play. And I remember we took a picture of the principal's head, and then we put it through a little app on an iPad by SolidWorks that immediately took the head and sliced it into 50 slices, right? And then we took each slice became its own 2D shape, and we printed them out. Put them into the laser cutter. Our bed was 2 foot by 3 foot, and cut out each shape, each individual piece, and then stacked them back up. And then we covered the thing with like plaster Paris and painted over it. So this was supposed to be our principal. It looked just like them. It's pretty cool. There's wood that's been engraved and cut, and it actually becomes flexible afterward, like it can bend. Kids making their own scientific instrumentation, making their own rulers, their own gauges, so to the exact sizes that they could use those as tools in class. More stencils, bubble wands. Oh, I love this. Sweet manufacturing. This was about designing a candy or a chocolate dessert, but that was going to have to address somebody's needs or wants for a health related issue. And so we looked at different ingredients like cinnamon and nuts and this and that, and like what different benefits do they have? And so part of this was them learning to use CAD software. So they would design their chocolate bar like in CAD, and come up with a design for this 3D thing that would be cast. And so we would cut the thing out of wood and put it into a vacuum former, and then vacuum form the plastic over top. And so we get the mold, right? And then we heated up chocolate and melted it on a hot plate, added ingredients, poured it into the mold, and cast the chocolate bar. And they had to make environmentally friendly or recycled packaging to go around. They had to brand the thing. That's not me, these are people from the class. Sweet manufacturing. And this is actually on that remote design challenges document I sent out with like 10 or 12 different remote design challenges. So we were 3D printing trophies. We would take a picture of a person and actually turn them into a 3D thing here. And we were making trophies up for different businesses in the area. So this was a design studio in Philly, and we had our kids make the trophies for their foosball tournament that they would hold between different design agencies in Philly once a year. Super cool. Look at these hipsters. Kids are using the plastic printer to make assistive devices that would make a tool easier to use or more efficient or help somebody with one hand. We talk about having empathy before you get into a design, the first step of the design process. You want to know what it's like. You want to make a prosthetic device for somebody with one arm? Cool. How do you get empathy for that? Tie a kid's arm behind their back for 3 days in school and have them write about the struggles that they didn't realize other people encountered that have that issue. That might be a form of capital punishment. I don't know if we can actually do that. I love buttons. I just used one of these for the first time. It was like $300 to get the button press and the parts. But then we had students designing buttons to raise awareness about endangered species that were being shown off at the zoo. And then the zoo gave out grant money for students to and awards for these projects that would raise awareness for the lemur monkey. And so they were designing these things. They had these posters that went with them and these flip books, and they went and showed these things off at the zoo. But then once we did this, then the button thing was there, and people were making button stuff nonstop. It's just their own thing, for fundraisers, for whatever. And it was a nice little investment just for $300, and once students learned how to use it. This is just a sampling. I have so many more things to show you guys, but I'm going to stop now so that this video doesn't take 3 days to buffer and upload. But I'm glad I got a chance to at least take you through some of this stuff here. And later on, maybe we'll look at some different makerspace components and designs from some different labs. what they have in them. And we'll get back to that. So thanks for your time today. I know this was really a long video, but I'm glad I had the chance to share some PBL experiences I've had in classrooms with you. And again, I got just as much to show you in a second video and a third. So that's it for now. I'm going to stop recording and I'll catch everybody later. Thanks again. Have a great day.